Hi, hello, good morning. This is Dr. Abdul Pasha, working as Assistant Professor, Institute of Aeronautical Engineering, Hyderabad, from Department of EEE. So, this is about the course of Power System Operation and Control. Here now I am going to discuss about the topic called Methods of Reactive Volt Amps Generation. So, here the reactive volt amp generation makes the power system to be stable. So here we will discuss some methods. So these are the methods of controllable reactive volt amp generation cases. These are variable impedance type static VAR generators, GTO thyristor controlled series capacitors called GCSC, thyristor controlled series capacitors called by the name TCSC, thyristor switched series capacitors TSSC, switching converter type VAR generators, static synchronous series compensators, SSC. So these are the most important methods they can make the VAR generation compensation. Coming to the first case, GTO thyristor controlled series capacitor, that is GCSC case. So here this elementary idea about GTO thyristor controlled series capacitor is proposed by Cardi with the others in 1992. So this diagram is represented here. So it contains a fixed capacitor in parallel with the GTO thyristor or equivalent to this, and that has the capability to turn off the command cases. It is having the switch type of arrangement here, and they are connected anti-parallel connection of thyristors that should be connected across one of the capacitor. So it is going to be represented with of the graphical representation. So the curve which will be starting with the capacitive compensation case with voltage across the capacitor at 0, and this should be taken as the reference from the basic fundamental case, and with this case it will generate at an angle of gamma. So the current that should be raised from the instant where it will be ends at Vc of gamma case. So here the objective of the GCSC is to control the AC voltage, that means voltage across the capacitor at a given current. That should be evidently that GTO valve switch is closed means voltage across the capacitor is 0, and when the valve is open it should be maximum. So for controlling the capacitor voltage, the closing and opening of the valve is going to be carried out in each half of the cycle in synchronism with the AC system frequency. So GTO valve is stipulated to close automatically through the appropriate control action. That means whenever the capacitor voltage is crossing the 0 limit, that means GTO valve is going to be axed together. So here we are supposed to recalling the thyristor valve of the TCR when it opens automatically. So whenever that current crosses to the 0 value. So however here the turn off instant of the valve in each half cycle is controlled by a delay angle called gamma, that is represented here. So this delay angle will represent the thyristor turn off situation. With respect to this, the peak moment of the line current is going to be follows. So wherever the line current and the capacitor voltage are represented with gamma equals to 0 at an arbitrary turn off delay angle case gamma, for the positive and negative half cycle it is going to be treated. So when the valve switch is opened, the crest of the line current, that is gamma, becomes 0. So resultant capacitor voltage Vc will be the same as that obtained in the steady state condition with permanently opens the switch. So when the opening contacts of the valve is delayed by the angle gamma with respect to the crest of the line current, so capacitor voltage can be expressed with a definite line current with the I of t case as I cos omega t. So when voltage across the capacitor is treated, 1 by c integral of v omega t, I of t dt is I by omega c sin omega t minus sin gamma. So since the interval opens at gamma and stipulated to close at the first voltage is going to be 0, it is valid for the interval in the range of gamma less than or equals to omega t less than or pi minus gamma case. So for subsequent positive half cycle intervals, the same expression remains will be valid. So for subsequent negative half cycle intervals, the sign of the terms becomes opposite in case. So it is evident that the magnitude of the capacitor voltage can be varied continuously by this method of turn off delay control from the maximum value, that is gamma equals to 0 to gamma equals to pi by 2. So where the capacitor voltage together with its fundamental component as supposed to be represented here in this diagram. So that makes the fundamental component of the wave here across each gamma angle 0 at gamma 1, gamma 2, gamma 3, gamma 4. Like that the instant wave follows further sequences to the extent of the line. So when it makes to the case, that means the adjustment of the capacitor voltage is similar to the adjustment of the thyristor controlled rectifier current case. So that is discrete in nature and it can take place only once in each half cycle case. So amplitude of the capacitor voltage is supposed to be represented by I by omega c 1 minus 2 gamma by pi minus 1 by pi sin 2 gamma. So here I is the amplitude of the line current. So C is the capacitance of the GTO thyristor, that should be controlled capacitor, and omega is the angular frequency of the whole AC system. So on the basis of the GCSE, we are going to vary the fundamental capacitor voltage at a fixed line current. That means it should be considered as variable capacitive impedance. So an effective capacitance impedance can be found for a given value of angle gamma. In other words, effective capacitance impedance Xc as a function of gamma for GCSC can be defined as Xc of gamma equals to 1 by omega c 1 minus 2 gamma by pi minus 1 by pi sin 2 gamma. So this is the instant where we can vary the values as from 0 to 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. So here from 0, 10, 20, 30, 40 up to 90 degrees gamma is considered. So the extent of the angle which should be varies like this, that is 1 minus 1 by pi sin 2 gamma. So 1 minus 2 by pi gamma leads to the case VCF of gamma case, that is 1 by pi c 1 minus 2 by pi gamma minus 1 by sin 2 gamma case. So this is the anti-parallel connection of the thyristor case connected across the capacitors combination. The resultant of the graphical representation represents minimal to the maximum current where this area is covered by all the portion of the line at leading capacitor VC of max. When percentage loss is considered, the curve may be rises like this and this may reaches to the 0 case, and when it is the case of B1, then the area surrounded by this region is represented with Imax with the net reactance of the capacitance as Xc. When loss is more in percentile, about 50%, then the graphical representation will be the boundaries covered by this region. So thyristor switched series capacitors. So here the basic arrangement of the thyristor switched series capacitors are shown. It contains a number of capacitors, each shunted by an appropriately rated bypass value that should be composed of string of reverse parallel connected thyristors in series. That means the series connection of anti-parallel connection of thyristors are shown with the C1, C2, Cm-1, Cm up to Cm. The voltage across this combination as Vc1, Vc2, Vcm-1 and up to Vcm, it is going to be treated. So its operation is different due to the imposed switching restrictions of the conventional thyristor valve case. So operating principle of the TSC is straightforward. That means degree of series compensation is controlled in a step-like manner by increasing or decreasing the number of series capacitors increased. So capacitor is inserted by turning off and it is bypassed by turning on the corresponding thyristor valve here. So a thyristor valve commutates naturally. So here making off of the thyristor process is usually known as one of the commutation process. So this makes the natural commutation that it turns off when the current crosses to the 0 value. So likewise a capacitor can be inserted into the line by the thyristor valve only at the 0 crossing of the line current case. So since the insertion of the capacitor takes place at the line current is 0, full half cycle of the line current will charge the capacitor from 0 to maximum, and the successive opposite polarity of half cycle of the line current will discharge it from the maximum to 0 case. So the capacitor insertion at line current is 0, that should be necessitated by the switching limitation of the thyristor valve, that results in a DC offset voltage which is equal to the amplitude of AC capacitor voltage. So here, in order to minimize the initial surge current in the valve and the corresponding circuit transients, thyristor valve should be turned on for a bypass section only when the capacitor voltage leads to 0 value. So with the prevailing of DC offset, this requirement can cause a delay up to 1 full cycle, which would be set to the theoretical limit for the attainable response time of the TSSC case. So here the characteristic showing TSSC means with 4 series connected compensator modules which are operated to control the compensating voltage. So for this compensation mode, reactance of the capacitor bank is selected so that it produces average rated compensating voltage. So here VC max is about a 4XC and with minimal current I minimum in the phase of decreasing the line current over a defined interval of I minimum less than or equals to I less than or equals to I max. So as the current I minimum is increased towards I max, the capacitor banks are progressively bypassed by the related thyristor valves to reduce the overall capacitive reactance. That should be in a step-like manner and thereby maintaining the compensating voltage with increasing line current case. So this is the diagram showing the anti-parallel connection of the thyristor acts as one of the switch combination connected across the capacitor in parallel. So when the switch is on, the curve may rises like this with maximum current and it will drop, so the curve will follows its continuity path. This is at VC equals to 0 case and the switch is allowed to turn on at VC equals to 0. So in the impedance compensation mode, TSSC is applied to maintain the maximum rated compensating reactant that should be at any line current up to the maximum rated value. So in this compensation technique, capacitive impedance is selected so that it can provide the maximum series compensation. That means at a rated current about 4XC equals to VC max by I max, the TSSC can vary in a step-like manner by passing one more capacitor banks. So loss versus line current characteristics for this compensation mode is also with 0 compensating impedance. So all the capacitor banks are bypassed by the thyristor valves itself. That means for maximum compensating impedance, all thyristor valves are off and all are inserted in such a manner that the voltage can be compensated sequentially. So this is the diagram showing for the compensation of the voltage with respect to the minimal current and maximum current. The capacitance that should be leading in nature with the VC max and the area that should be occupied by these boundaries may supposed to be represented in such a manner. And losses are going to be taken in percentile, that means 0.5, then VC becomes 0, the boundaries that occupies about VC max case. And here it is about the region which should be covered with XC max, that capacitive reactance will be maximum with the maximum current. And this is the value with XC equals to 0, that means the boundaries which will occupy at maximum value about 0.5 region. So what are the advantages of TCSC? Thyristor controlled series capacitor means use of thyristor controls in series capacitors are potentially offers the following advantage. They are rapid continuous control of the transmission line, series compensation levels, and dynamic control is achieved with this power flow in selected transmission lines. So within the network it can enable to optimal power flow conditions and it can prevent the loop of the power flow case. So damping of the power swings from local and inter-area oscillations are going to be taken place. So suppression of subsynchronous oscillations are treated. So at subsynchronous frequencies, TCSC presents an inherently resistive inductive reactance. That means the subsynchronous oscillations cannot be sustained in this situation, and consequently they go under damping cases. So decreasing the DC offset voltage about invariably resulting from the insertion of series capacitors that can be made to decay very quickly within the few cycles from the firing control of the TCSC thyristors cases. So enhanced levels of protection for series capacitors is going to be done with the fast bypassing of the series capacitors that can be achieved through the thyristor control when large over voltages are developing across the capacitors. So they follow the faults and they will ready to interrupt the faults and make the compensation easy. Likewise, capacitors can be quickly reinserted by the one of the thyristor action after fault clearing that should be aided into the system stabilization case. So voltage support is provided here with this TCSC in addition with the series capacitors that can generate reactive power that will increases the line loading, thereby aiding the regulation of the local network voltage. And in addition to that, elevation of any voltage instability is going to be taken place. So reduction of the short circuit current during events of high short circuit current takes place. So TCSC can switch from controllable capacitance to controllable inductance mode, thereby restricting to the short circuit currents. So here the basic conceptual of TCSC module comprises a series capacitor C that should be in parallel with the thyristor controlled reactor L. So here line current is passing from this instant as IC, and this should be passing to the capacitor that is connected across this switch combination of anti-parallel connected two thyristors named T1 and T2. One of the inductor is connected to this switch in series that should be treated as one of the thyristor current IT here. So what is the basic principle involved here for TCSC means this is a series controlled capacitive reactance that can provide continuous control of power on the AC line over a wide range. So from the system viewpoint of view, the principle of variable series compensation is simply to increase the fundamental frequency voltage levels across the fixed capacitor in a series compensated line that should be happens through the appropriate variation of the firing angle alpha, that is this one. So this enhanced voltage can changes the effective value of the series capacitive reactance. So this is the diagram which is showing as inductor is connected across the capacitor. So due to this, impedance of the LC network is developed. That equivalent impedance may be combination of this XC XL by XC plus XL combination. Omega L is greater than 1 by omega C, then the reactance of the FC is less than that of the parallel connected variable reactor, and that this combination provides a variable capacitor reactance that are both implied together. So moreover, the inductor is ready to increase the equivalent capacitive reactance of the LC combination as FC existing. So if omega C minus 1 by omega L equals to 0, a resonance develops that results in an infinite capacitance impedance. That should be obviously unacceptable condition. So however, omega L less than 1 by omega C, LC combination provides inductance above the values of the fixed capacitor and inductor cases. So here the situation which is corresponding to the inductive linear mode of the TCS operation. So in this variable capacitor mode of the TCSC, as the inductive reactance of the variable inductor is going to increases. So equivalency of that capacitive reactance is gradually decreases. So minimum equivalent capacitive reactance is obtained for extremely large inductive reactance where the variable inductor is open circuit. So here in which the valve is equal to the reactance of the fixed capacitor itself. That means behavior of the TCSC is similar to that of the parallel LC combination. So difference obtained here that LC combination analysis is based on the presence of pure sinusoidal voltage and also current in the circuit, whereas in the TCSC, because of the voltage and current in the FC mode, thyristor controlled reactors are not sinusoidal because of thyristor switching cases. So here are some of the modes of TCSC operation: bypassed thyristor mode 1 and blocked thyristor mode, partially conducting thyristor or vernier mode. What is bypassed thyristor mode means? In this bypassed thyristor mode, thyristors are made to fully conduct with a conduction angle of 180 degrees. This is 180 degrees. So gate pulses are applied as soon as the voltage across the thyristor that reaches to the zero and reaches to becomes positive results in a continuous sinusoidal of the flow current throughout the thyristor valves. So TCSC module behaves like a parallel capacitor inductor combination. So however, net current through the module is inductive in nature. So for the susceptance of the reactor, it is selected such that it should be greater than that of the capacitor. So this is also known as the thyristor switched reactor, and by the bypassed thyristor mode, it is very distinct from the bypassed breaker mode, in which circuit breaker is provided across the series capacitor and is closed to remove the capacitor or TCSC module in the event of TCSC faults or transient over voltage across the TCSC takes place. So this mode is employed for control purposes and also for initiating certain protective functions. So whenever there is a TCSC module bypassed from the violation of the current limit, finite time delay, that is TD, must elapse before the module that can be reinserted after the line current which falls below the specified limit. So this is the limit where we can expect for the fault current. So here anti-parallel combination is connected in series with this inductor case and the capacitor is supposed to occupy. So blocked thyristor modes are taken place. In this mode, it is also known as waiting mode. The firing pulses to the thyristor valves are blocked. If the thyristors are conducting and a blocking command is given, thyristors turns off as soon as the current through them reaches to a zero crossing value. So TCSC module is thus reduced to a fixed series capacitor and the net TCSC reactance is capacitive in nature. In this mode, DC offset voltage of the capacitors are monitored and quickly discharged using a DC offset control without causing any harm to the transmission system transformers. So likewise, it is connected in parallel to the whole of the capacitor combination with the set of series combination of switched thyristors. So what about partially conducting thyristor or Vernier mode of operation means? This allows the thyristor control switch capacitor to behave either as a continuously controllable capacitor reactance or continuously controllable inductive reactance. So it is achieved suitably by varying the thyristor pair firing angle to the appropriate range. So however, smooth transition from capacitive to inductive mode is permitted because resonant region is in between the two modes. So variant of this mode is the capacitive Vernier control mode. So in which thyristors are fired when the capacitor voltage and capacitor currents have that opposite polarity in nature. So this condition can cause TCR current that has a direction opposite to that of the capacitor current. So thereby which will result in a loop current flow in the TCSC controller. So loop current increases the voltage across the fixed capacitor that will effectively enhancing the equivalent capacitive reactance and the series compensation of the level for the same value of the line current is taken place. So to preclude that resonance factor, firing angle alpha of the forward facing thyristor as measured from the positive reaching to a zero crossing of the capacitor voltage is constrained in the range of alpha minimum to the alpha max. So this constraint provides a continuous Vernier control of the TCSC module reactance. So the loop current increases as alpha is decreased from 180 degrees to alpha minimum. So maximum TCSC reactance is permissible with alpha equals to alpha minimum, which is typically 2.5 to 3 times the capacitive reactance at fundamental frequency range. So another variant is situated as inductive Vernier mode, in which the TCSC can be operated by having a high level of thyristor conduction. So what happens in this mode means direction of the circulating currents are reversed and the controller presents a net inductive impedance. So that is shown here. This is the path where the current is existing. Here it takes the reverse direction. So based on the 3 modes of the thyristor valves operation, 2 variants of the TCSC they emerges. So thyristor switched series capacitors which permits a discrete control of the capacitive reactance. So thyristor control series capacitors offers a continuous control of capacitive or inductive reactance. That means It is, however, more commonly employed. So, what is the analysis of the TCSC here means? The analysis of the TCSC operation in the vernier control mode is performed, that is based on the simplified TCSC circuit case. So, transmission line current is assumed to be independent input variable and is modeled as external current source, IS of T. So it is further assumed that the line current is sinusoidal in nature as it is derived from the actual measurements, demonstrating that very few harmonics exist in the whole line current. So however, that analysis is presented that may be erroneous to the extent that the line current deviates from the purely sinusoidal in nature. So this is the diagram how series compensation is done. So for this the current source is connected across this capacitor with one of the switch combination that is supported by inductor arrangement. So current through the fixed series capacitor is expressed as C into dV by dt as Is of t minus It of t into U. So switching variable is 1 when the thyristor valves are conducting in nature. When the switch is closed, on the other hand, U becomes 0. When the thyristors are blocked when switch is open. So thyristor valve current is then described L into di by dt into Vc into U. So line current will be represented by Is of t equals to I cos omega t. This is the combination. So here the equations to be solving with the knowledge of the instant of switching cases. In equidistant firing pulses control for balanced TCSC operation, thyristors switched on twice in each cycle of the line current at instant T1 and T3, that is given by T1 equals to minus beta by omega and T3 equals to pi minus beta by omega case. Here beta is the angle of advance before the forward voltage becomes 0, or we may treat beta equals to pi minus alpha, that is 0 to beta max, 0 less than or equals to beta less than or equals to beta max. So firing angle is generated using a reference signal that can be in phase with the capacitor voltage. So thyristor is switched turns off at the instant T2 and T4, that will be defined as T2 as T1 plus sigma by omega and T4, that is equals T3 plus sigma by omega. So sigma is the conduction angle which is assumed to be the same in both the positive and the negative cycles of conduction. This is also 2 beta case. So solving for TCSC expressions which may result in steady state thyristor currents, that is k square by k square minus 2 into cos omega t minus cos beta by cos k beta to cos omega t. So here omega is 1 by root LC. So k equals to omega r by omega is equals to 1 by omega L into 1 by omega C case, that is Xc by XL. So Xc is the nominal reactance of the fixed capacitor only. So steady state capacitor voltage at the instant of omega t equals to minus beta gives Vc1 equals to Im Xc by k square minus 1. So sin beta minus k cos beta tan beta will be exist. At omega t equals to beta it becomes 0. Capacitor voltage is represented by omega t equals to beta, that is equals to Vc2 as minus Vc1. So capacitor voltage is finally obtained as Vc of t equals to Im Xc by k square minus 1 into minus sin omega t plus k cos beta by cos k beta sin omega t. So Vc of t is Vc2 plus Im Xc sin omega t minus sin beta. Because the non-sinusoidal capacitor voltage, it has odd symmetry about the axis omega t 0. So fundamental component is obtained as Vcf equals to 4 by pi integral of 0 to pi by 2 Vt sin omega t d omega. So XTCSC equals to Vcf by Im. So XTCF Vcf by Im gives Xc minus this value. So this will be as 2 beta plus sin 2 beta by pi. So 4xc square by Xc minus XL with cos square beta can be obtained with tan k beta minus tan beta by pi. So this is the graph that is representing as inductive nature and this is the capacitive nature. They will be separated oppositely and the capacitive mode is existing with 150 degrees angle. So during that instant the outputs generated will be like this. This will follows usually for TCS voltage. As the line current is the factor, the current will start from here instant and it will exist. And it is the capacitor current, it may starts like this, capacitor current. So the variations are supposed to be expected in capacitive mode for an angle of alpha 150 degrees. When this is the series compensation, TCR current may be represented with IARE EVA. During this inductive mode, alpha becomes 130 degrees. Then that instant which follows here. At this instant, the range of TCSC voltage follows in kiloamps ranges. So that current may be vary suitably to the extent in various aspects. So here basic operation control schemes for TCSC and TCSC are generated. So for that function of the operating or internal control variable impedance, it is to provide appropriate gate drive. The thyristor valve is to produce compensating voltage or impedance defined by a simple reference. So internal control operates the power circuit of the series compensator, which will enable its function to self-sufficient manner as a variable reactive impedance cases. So thus power circuit of the series compensator together with the internal control can be viewed as a black box impedance amplifier, the output of which can be varied from the input with a low power reference signal. So reference to that internal control is provided by external or system control. So here whose function is to operate controllable reactive impedance so as to accomplish to the specified compensation objectives of the transmission line case. So likewise external control receives line impedance, current, power or angle reference end, and within that measured system variables it derives the operating reference for the internal control action. So structurally the internal controls for the three variable impedances type compensators like GCSC, TCSC, TSSC could be similar in nature. So strictly the function is simply to define the conduction or blocking intervals of the valve in relation to the fundamental case component of the line current may exist. So this requires the execution of three basic functions: synchronization to the line current, turn on or turn off delay angle computation, gate signal generation. These functions obviously can be implemented by different circuit approaches with the different advantages and disadvantages. In the following three possible internal control schemes, functionality, one for GCSC and the other two for the TCSC power circuit arrangements. So either of the TCSC schemes they can be adopted for subsynchronous resonance. They should be applicable in nature. So internal control scheme for the GCSC is derived here. This is the synchronous timing circuit with the PLL arrangement, and a capacitor voltage sensing and processing circuit is derived. So these both combinations are coupled together with the voltage to turn off delay angle compensator with the converter. This is done with one of the angle delay gamma as K into F as gamma case, which is connected to one of the gate drive control. So this arrangement is made connected across the parallel circuit with anti-parallel connection of the thyristor combination. This is the input curve, whatever we consider. According to that, the pulses generated. These are the pulse generations. So here the response of the output may be like this, and again the valve is turned off. Same peaks we may expect for this. So this is the omega t case, and when the power is in valve in on state mode, then the number of peaks extend its area. So first function is the synchronous timing here. That should be provided by phase locked loop circuit that runs in synchronism with the line current case. Second function is the reactive voltage or impedance. This is to turn off delay angle conversion according to the relationship respectively. So third function is the determination of the instant of valve turn on when the capacitor voltage becomes 0. This function may also include maintenance of a minimum on time at a voltage 0 crossing levels. This is to ensure immunity to subsynchronous resonance case. So fourth function is the generation of suitable turn off and turn on pulses for the GTO valve. So basic GCSC power circuit has internal control that can be considered as a controllable series capacitor which is in response to the transmission line current, which will reproduce the compensating impedance defined by the reference input. So dynamic performance of the GCSC is similar to that of the TCR circuit, that both have the maximum transport lag of one of the half cycle. So internal control scheme for the TCSC, the main considerations for the structure of the internal control system is, as the TCSC is to ensure immunity to subsynchronous resonance case. So here present approaches follows two basic control philosophies. So one is to operate the basic phase lock loop from the fundamental component of the line current, that with error amplifier, PI controller, and a synchronous time circuit. This is with filter and phase correction circuits. So current to delay the angle converter, here gate pulse is to generation. All this combination is connected to the inductor case. So reference signal is ready to excite the voltage case. So this will represent functional internal control structure for the TCSC, that is based on the synchronization, the fundamental component of the line current case. So in order to achieve all these aspects, it is necessary to provide substantial filtering to remove the super and in particular the subsynchronous components from the line current, and at the same time maintain correct phase relationship for the proper synchronization operation. That means possible internal control schemes of this is going to be achieved. That is, in this arrangement, conventional technique of converting the demanded DC current into the corresponding delay angle, which is measured from peak with a fixed 90 degrees from zero crossing, is taken to the fundamental line current. That should be used. So reference for the demanded TCR current is usually provided by regulation loop of the external control case. So which compares the actual capacitive impedance or compensating voltage to the reference that should be given for the desired system operation. So second approach also employs to a PLL. That means synchronization to the line current for the generation of the basic timing reference considered. So however, in this method, actual zero crossing of the capacitor voltage is estimated from prevailing the capacitor voltage and also line current. That should be done by one of the angle correction measurement circuit. So now delay angle is then determined from the desired angle and estimated correction angle. So this is so as to make the TCR conduction, and that should be symmetrical in nature with respect to the expected zero crossing value. So desired delay angle in this scheme can be adjusted by a closed loop control system. That is basic time reference provided by the PLL circuit. So delay angle of the TCR and thus compensating capacitive voltage in the previous case. That is controlled overall by regulating the loop to the external control in order to meet the system operating requirements. So this regulation loop is relatively slow with a bandwidth that is sufficient to meet the compensation requirements. So power flow adjustment, power oscillation damping can be done easily. So with these all analysis from the standard point of view, angle correction circuit, which by comparison is very fast, that correction takes place in each half cycle. The output of the phase shifter is almost steady state in nature. So although the control circuit performances are usually heavily dependent on the actual implementation, so second approach theoretically more likely to provide faster response. This is for the application requiring such response. That means error amplifier as PI controller, and this is the signal generation as synchronous timing PLL circuit is connected here. So that controllable phase shifter is provided as advanced or retard. That may be current I with VC angle correction circuits. This whole arrangement treated as a TCR gating control, that gate pulse generator, and the TCSC can be controlled over this system. So functional internal control scheme for the TCSC is based on the prediction of the capacitor voltage that should be reaching to the zero crossings. So these are some of the references whichever I have taken, and this gives the more information regarding all the controllable variables which makes the system to be stable. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.